Okay, let's dive into this. Have you ever wondered how computers actually make predictions from massive piles of raw data? I mean, it is incredibly easy to assume that machine learning requires pages of intimidating math, deep calculus, and incomprehensible equations. But today, we're going to look at a foundational algorithm that completely flips that assumption on its head. Welcome to this explainer on K-nearest neighbors, where we'll demystify one of the most intuitive and honestly most powerful concepts in the world of data science. Here is our roadmap for today. First, we'll meet K-nearest neighbors. Second, we'll cover how the algorithm actually works. Third, we'll look at distance metrics and K-values. Fourth, we'll weigh its strengths, weaknesses, and comparisons. And fifth, we'll wrap up with real-world applications and the future. Let's get started. Section 1. Meet K-nearest neighbors. You know, this algorithm completely challenges the perception that machine learning requires dense, incomprehensible formulas just to get off the ground. KNN, or KNN for short, is a supervised machine learning algorithm. It makes predictions based purely on the similarity between data points. But the real kicker here is the second part of that definition. It does not build a mathematical model during training. While most machine learning models spend hours, quote-unquote, learning and building a complex formula behind the scenes, KNN doesn't do that at all. It operates entirely on that old logic that birds of a feather flock together. It learns simply by comparing new data directly to existing data. Let me give you a highly relatable example to make this super concrete. Imagine you're standing in front of a table, and right there on that table is a basket filled with apples and oranges. Now, I place a brand new, unknown fruit on the table right next to the basket. How does the algorithm decide what this new fruit is? Well, it simply measures how close the new fruit is to the existing ones. If most of the fruits sitting nearby are apples, the algorithm confidently declares that the new fruit is an apple. If most of the nearby fruits are oranges, it's classified as an orange. It's practically toddler-level logic, but mathematically, it is incredibly effective. That is exactly how KNN makes its classification decisions. Section 2. How the algorithm works. Now, what's really interesting about this is the surprisingly simple procedural core of the algorithm. Let's walk step by step through the exact life cycle of a single data point as it enters and gets processed. Step 1. Store training data. Remember, there's no complex model building phase here. The algorithm literally just memorizes all the data it is given. Step 2. Choose K. This is where we tell the algorithm exactly how many neighbors it should look at. Step 3. Calculate distance. When a new piece of data comes in, the algorithm measures its exact distance from every single stored training example. Step 4. Find nearest neighbors. It gathers up the K number of closest points. And finally, Step 5. Make prediction, based entirely on what those closest points are. It is just incredibly elegant in its simplicity. But how exactly does it make that final prediction in Step 5? Well, it adapts perfectly to the type of problem you're trying to solve. You see, KNN handles both classification and regression. If we're doing classification, like deciding if an email is spam or not spam, it uses majority voting. The category with the most votes among the nearest neighbors simply wins. But if we're doing regression, which means predicting a numerical value, like a house price or tomorrow's temperature, it doesn't vote. Instead, it calculates the average value of those nearest neighbors. It's a brilliant way to handle both categorical and numerical data. Section 3. Distance metrics and K-values. Now, all of this begs a massive, fundamental question. How does the computer actually know what the word close really means? It turns out close can mean a few different things. To calculate distance, KNN relies on these essential metrics. First, we have Euclidean distance. This is the most commonly used metric. It simply measures the straight line distance between 2 points. Think of it as how a crow flies. Next is Manhattan distance. Imagine you're driving through the grid-like city streets of Manhattan. You can't drive diagonally through buildings, right? You have to move horizontally and vertically, block by block. Finally, there's Minkowski distance, which is a flexible general mathematical form that can actually encompass both Euclidean and Manhattan distances, giving you greater flexibility depending on your specific dataset. But here's the thing, measuring distance is only half the battle. You also have to choose your K, the exact number of neighbors to look at. And this is a very delicate balancing act. If you choose a small K, like just one single neighbor, your prediction becomes highly sensitive to noise. If that single closest neighbor happens to be an error or a weird outlier, your prediction will be completely unstable. On the flip side, if you choose a large K, like 25, the model becomes way too general and it completely overlooks the subtle, important local patterns hiding in the data. So, the crucial point is that moderate values are commonly the sweet spot. Numbers like 3, 5, or 7 are frequently used by practitioners to balance out the noise without losing the local detail. The absolute best value always depends on testing it against your specific dataset to see what yields the highest accuracy.
Section 4. Strengths, weaknesses, and comparisons. Let's be real, machine learning isn't magic, and every algorithm has its trade-offs.
It's time for a completely objective reality check on where KNN shines and where it struggles. On the advantages side, KNN is wonderfully easy to implement and requires very little mathematical complexity. Because there is no training phase, it adapts instantly to new data. But look at the limitations. Because it basically memorizes everything, it has incredibly high memory usage. And because it has to calculate the distance to every single stored data point whenever a new prediction is requested, it is notoriously slow on large datasets. It saves you time up front, but it is computationally expensive right at the exact moment you want your answer. So how does it actually stack up side by side against the broader machine learning landscape? Compared to logistic regression, which is fast and best for linear classification, KNN handles nonlinear boundaries better, but at the massive cost of speed. Compared to decision trees, which build highly visual rule-based structures, KNN relies on raw similarity and has no tree construction at all. And compared to random forests, which are highly accurate ensembles of trees that predict incredibly fast, KNN is a much simpler algorithm, but will lag significantly in prediction time on large data. Section 5. Real-world applications and future. Let's zoom out from the mechanics to see how this simple, foundational logic actually impacts massive global industries. Have you ever wondered how online stores know exactly what to recommend to you? An online shopping website actively compares your purchasing behavior with the behavior of thousands of other customers. It literally finds the nearest neighbors to your profile, the people who buy exactly what you buy. If those similar people recently bought a specific new product, the algorithm immediately recommends that product to you. And this brilliantly illustrates how direct similarity is working behind the scenes of your everyday life. But the sheer versatility of an algorithm that relies solely on measuring distance is staggering. In healthcare, it's used for disease diagnosis and medical image classification. In computer vision, it powers things like face and handwriting recognition. In finance, it's utilized for credit scoring and flagging unusual behavior for fraud detection. Even in agriculture, it helps classify crops and analyze soil composition. And despite all the recent hype around newer technologies, just look at this quote. Even with the growth of deep learning, KNN continues to be valuable. It serves as a strong baseline algorithm. Machine learning practitioners still heavily rely on it because it performs so well on small and medium data sets, and because it is just so quick to implement, it remains the absolute perfect tool for rapid prototyping and establishing a really strong educational foundation. Which leaves us with this final provocative thought. In an age of hyper-complex deep learning, neural networks, and massive artificial intelligence models, why does a simple compare and contrast algorithm remain so vital to our future? Well, perhaps it's because, at the end of the day, some of the most powerful and reliable insights come not from abstract equations, but from simply observing what is closest to us. Thank you for joining this explainer. Keep questioning, keep learning, and we'll see you next time.